My name's Harry Hockheiser. I'm the director of the MIDAS Center. And it's my pleasure to welcome Matthew Wascher. I hope I got that right. As our speaker today. Dr. Wascher received his PhD in statistics from the Ohio State University. We have to make sure we say the there. We also spent a year as a postdoctoral scholar in the Mathematical Biosciences Institute there. In 2021, Dr. Wascher joined the Department of Mathematics at the University of Dayton, literally, I think, right down the road from the Ohio State University, if I'm not mistaken, just about an hour or so away. And his research interests lie in the applications of probability and statistics to problems in biology and public health. Today, he's going to speak to us on monitoring disease transmission and prevalence in a closed population under repeated testing. So I'm looking forward to hearing this. And Matthew, please take it away.
Well, thanks for inviting me, and thanks for the nice introduction. So as was said, so I got my degree from Ohio State in 2020, and that was a terrible time to graduate because there were no jobs that year. They all got canceled. And so Ohio State's like, well, you've been working on modeling infectious disease. This whole COVID thing has happened. We'll keep you on for a year and you can work on our COVID response team. That's actually what I did for that year. Most of my work was on the COVID response team. So it was very challenging, but also very interesting, and a lot of cool stuff came out of that. And so what I'm going to talk to you about today is a project that came out of some models we built for the Ohio State that were actually used for monitoring COVID on campus. And so let me bring up my slides and I can tell you a bit about what we were doing and get started here. Let's see, share my screen. Okay, let's full screen this. Okay. So here are some of my collaborators that were on the comprehensive monitoring team at OSU. So Wascher is now at University of Nottingham.
Matt,
he was a postdoc with me at the time. Patrick Schnell is in the College of Health.
Matt, we can only still see your Acrobat window here. We're not seeing the full screen, and we're not seeing anything about your collaborators. That's better. Thank you.
Really, you can't see the full screen?
Now we can.
Let me try one more time. So,
no,
all right, let me see if I full screen it and share that.
Now we can see it.
One more time.
It's coming across.
Yeah, we can see it.
Okay, great. So I don't know what happened there, but problem solved, I guess. So Greg Rampala, also in the College of Public Health at Ohio State. Joe Tiem is kind of like the head of the modeling section of this we call the CMT. And then Mikkel Kvam was the head of our contact tracing, did a lot of sort of boots on the ground type work as far as organizing those kind of things. So I worked with all these people on this work I'll show you today, and they were, working closely throughout the pandemic. It was kind of, a bonding experience, given all the craziness and tight deadlines and sort of all those things that were happening. So I got to know them all very well and had a great experience working with all of them. So thanks to them as well. Okay, so I'll talk today about some work we implemented at OSU as part of the efforts to control transmission and prevalence on campus. And so Ohio State's strategy was to have a repeated testing scheme. So the idea was we have these students living on campus. We come back after closing down, March 2020, or back, it's now fall 2020, and we'll say every student must test once per week. If you test positive, you isolate for 2 weeks, later reduce to 10 days based on CDC guidelines, but it's not that important. And so the idea was, well, if we're doing this, we want to build a model where we can estimate prevalence and transmission in this scenario. And part of the idea behind removing people is to both, well, testing gets you an idea of what prevalence is, and removals are also supposed to help control prevalence. We can find people that are infected quickly is the idea and isolate them. And that will help reduce the spread of infection on campus, because as you guys know, probably Ohio State, big school, lots of parties, football, these things that could potentially create super spreader events. Want to crack down on that, make sure that's not going to blow things up, send us all home. Okay, so a couple modeling considerations. If we're going to do this, we actually get a time series of tests and results for each individual. So it's not like your sort of classic test a simple random sample of people. I actually am tracking the people over time. Likewise, everyone's testing regardless of symptoms or exposure. Even if you don't think you were exposed, still got to do your weekly test. And also, so at least at the time was believed, 1 week, this is sort of pre-vaccination, ancestral and later, I think, alpha COVID. 1 week is shorter than your typical recovery time for COVID-19. So what does that mean? If someone gets sick, there's a good chance we'll test them while they're infectious or while they're infected. And then also behavior might change over time. A big concern was football games, obviously. It's a sort of a big partying hub at OSU. Things like finals, various things can happen where students' behavior might change over time. So the question was, how can we account for, leverage the information in these considerations? So if you're just going to sort of think about, well, I have a random sample of people I test and I want to estimate prevalence, your sort of simple estimate, I'll call the naive estimate, is to say, well, my prevalence hat is I do I total tests on, or I have some number of total tests on day I, look at how many are positive. Prevalence is simply that ratio. It's my estimate of prevalence, simple sort of binomial model. Obviously, if you were testing a simple random sample, nothing wrong with doing this, very, very sound thing to do. But for us, there's a couple problems here. So for one, if we have this time series information, we want to actually use that information. We don't want to just throw it away. We want to follow people over time, recognize we're testing the same person repeatedly. And then secondly, it turns out this actually is biased under our testing regime. When you have this repeat testing regime with removals, this estimator ends up being biased. And so I'll talk about why, and it makes a lot of sense once you hear about it. But it seems like something people weren't really thinking about or weren't really aware of, at least as far as we can tell, as far as reading literature, talking to our colleagues. Okay, so why do you get this bias? Well, here's a very simple toy example. Suppose that in this example, over the weekend, I have 15 people and 5 of them get infected over the weekend. Then over the course of the weekdays, I'm testing 3 of them each weekday, sort of going across the population. If you test positive, you get removed at the start of the next day. And we'll assume, for the sake of simplicity, no new infections during the week, just to make our lives sort of simple here, obviously not realistic, but just for the sake of this example. So on Monday, I test people 1, 2, and 3. Prevalence is 1/3. That's right. Then I remove person 2 the next day. On Tuesday, I test 4, 5, and 6. Prevalence estimate still 1/3, but actual prevalence is now 4 out of 14 because I removed that person. Then Wednesday, test person 7, 8, and 9. Prevalence is still 1/3, or sorry, prevalence estimator positivity is still 1/3. Actual prevalence is now 3 out of 13. Thursday, test person 10, 11, 12. Prevalence estimate is still 1/3. Actual prevalence is 2 out of 12. And then lastly, Friday, test person 13, 14, 15. Prevalence estimator still 1/3. Actual prevalence 1 out of 11. Because the idea here being prevalence we care about is of people who are not isolated, not removed from the population, what percent of those people are infectious? That's what we care about. And as you can see, over the course of the week, the estimator becomes sort of more and more upward biased because of these removals. So it makes a lot of sense, but it seemed like people weren't really thinking about this, weren't really maybe always aware of this. And it's a thing that's very relevant to our scenario and our testing methodology here. So that's a very simple toy example. In general, the bias can be more complicated. For one, it depends on your testing schedule. Like here, I'm testing 3 each day over the course of the week. I could do other testing schedules, and you can find ones that give you various biases, some that are unbiased. Like if I test simple random sample each day, that's going to be unbiased. You can make it go upward, you can make it go downward. It tends to be an upward bias though, because usually you'll prioritize testing people you tested less recently, right? Because you have less information about them. And if you do that, well, they've had sort of more time to be exposed compared to people that you tested more recently since you've last observed them being, say, healthy if they weren't removed. So that's kind of what's driving this upward bias. We actually have a second paper focusing more on the bias itself, sort of the mathematics behind it, rigorously deriving a model for this, explaining how this bias arises, analyzing it in various situations, and ultimately driving a sort of model-free or transmission model-free estimator to overcome the bias, now available in JASA. So if you're interested, check that paper out, or you can ask me about it later. I'm happy to talk about it. But I'll focus here more on not so much this bias itself, what we did at Ohio State, which had some other considerations as well. All right. And here's an example, a simulation example showing this bias can actually be quite substantial in magnitude. So I simulated here some sort of a classic, SIR epidemic, and then I did a Poisson regression fit to it. So you can see I have the naive prevalence estimate, which is simply my number of positive tests divided by number of tests each day. I have this Poisson regression offset equal to the number of tests, and you can see the quantiles of that. And we're overestimating at the peak testing infections by about 30%. So quite substantial overestimate here you can see. And you can also see the sort of oscillating pattern here. because I have this kind of weekly testing schedule, like I did in my example. So usually on sort of Monday when things start, you're okay, and as the week goes on, things get worse and worse as far as the bias getting larger and larger. Then at the beginning of the week, again, it resets. So that's based on my testing schedule being everyone tests once per week on a random day. That's where that comes from. But the point is that it can be quite substantial in magnitude. It's not just sort of a throwaway, oh, a tiny bias we don't care about. Okay, so for Ohio State, we want to estimate just as prevalence, but also transmission. Therefore, you got to have a transmission model. And so we'll fall back on our classic, SIR type model, but just to be fully thorough here. So what do we have in our model? We'll model individual states. People can be like, for example, infected, healthy, isolated, whatever. You have events, so infections, recoveries, isolations. We have to have transition rules or parameters. And then those with some probability often called as a contact process, the idea being that infection events occur only between individuals who have contact, people who are neighbors in some network structure or some community structure is the idea. And of course, the most well-known is probably the SCIR model, which we're going to use here. So the idea is you have your 4 states: S, susceptible, you're currently healthy, but you could get infected, you're susceptible to the infection. Exposed, the idea here is that you've been infected, but you're sort of in the incubation period. There's some waiting time until you actually become infectious and able to infect others. Infectious, you're currently sick, you can infect others. And lastly, removed, you're either recovered or you're immune or you're isolated or whatever reason. But so once you've had COVID once in this model, you can't get it again, at least over the course of 1 semester. And given a semester is like 4 months long, we thought that was a pretty reasonable assumption for a single semester. Also, this is fall 2020. There aren't really a lot of vaccinations floating around yet. So we weren't too worried about things like pre-existing immunity. At that point, most people had not had COVID and there was not a lot of vaccination floating around. So. And then, of course, you want to be fully general. How do you parameterize these transitions? Well, you have sort of transition parameters for each kind of transition. So I have this, beta parameter. I can call it, to be fully general, beta T if I and J is saying it governs infectious contact for a pair of individuals I and J at time T. I could have gamma T of I, that's governing natural recovery for individual I at time T. And then I'll have this phi T of I, governing transitions from E to I for individual I at time T. And these could really be whatever you want. They can depend on T, they can depend on the IJ pair, they can depend on I, but it's often hard to observe that individual level information on a large scale. So people often take the sort of simple case of things being for one uniform across time, uniform across individuals pairs, and often also to be exponential or geometric rates. The idea there being then you get a Markov process, so I don't really have to worry about the past. As long as I have the present, I can describe probabilistically the future events. So your classic sort of SIR model, either the ODE formulation or the sort of count model, both those things follow these simplifications generally. Okay, and so our strategy was going to be what's called dynamic survival analysis. Actually goes back to Gillespie, for the Gillespie algorithm, which I'm guessing many of you are familiar with. But the idea is that instead of looking at counts of people infected at each period in time, we could follow an individual across time and say, what's that individual's survival function? So the idea is I have some individual I, and there's some time capital T of I, where individual I becomes infected, with T of I being infinity if it never happens. And then I define this script ST to be, well, what's the probability capital T of I is bigger than little t? What's the probability individual I has survived till time little t as a susceptible individual? And my colleagues, Wascher and some of my other colleagues, a paper where they proved that under appropriate assumptions, this can characterize not only an individual, but it characterizes the decay of S overall in the population. So sort of it's also fine to use it in a large population, at least, as characterizing the proportion of people that are currently susceptible. And so why is this a good fit for us? Well, because we have this time series data, it's a very natural way of thinking about things. So suppose, for example, for a minute that I knew what this survival function was. So I'm saying ST is probability individual L, survived susceptible until time T. But I have individual L's time series of tests. And we'll assume for now that our test is perfectly accurate. So there's no false positive, no false negatives. But assuming that's true, then suppose individual L tested positive on day J, and they most recently tested negative on day I. Then what can I say about when they became infected? Well, for each k between I and j, I can say that if I look at the quantity s sub k minus 1 minus s sub k over s sub I minus s sub j, well, that describes the probability individual L became infected on day k, conditional on knowing the survival function s. So if I have the survival function, I have perfect testing, I can impute the infection time probabilistically. And that's the principle that we'll use to adapt this idea of DSA to our motivating example of repeated testing, where I have this sort of interval censored observation of infection times based on my testing data. A few other things to think about. So we'll make some assumptions or sort of things to think about. So one is we'll assume a closed and well-mixed population. Is that true? Probably not. Generally, it's not true. But the issue is that it's often very hard to observe mixing patterns in populations in practice because, well, it's just hard to observe. You can do things like we had some sort of Wi-Fi based data, some location data from phones, but it's very hard to observe that at a really granular level. I can really say, oh, the network is going to be X. Usually we just make some large scale assumptions. And closed and well mixed is the simplest, but you can also show that under appropriate conditions, things like a Poisson network don't really behave any differently. So we weren't too worried about that. I'd also say that, well, I don't think closed and well mixed is accurate. Undergrads on campus are probably more homogenous than many populations people work with, like probably more so than the city of Columbus or the state of Ohio. Ohio State undergrads are probably more homogenous as a group than those people, so maybe a little bit closer to reality anyway. We have our infection parameter beta. We'll call it beta T and allow it to change over time. The idea is we think behavior is going to change over time, and we can't really necessarily predict or explain ahead of time how. So the idea is allowing beta to be beta T abstracts that a little bit. So it says, well, the parameter governing contacts changing over time. We're not really going to try and explain why it's changing, just to try and capture how it's affecting dynamics of infection on campus. Of course, things like football games would be a big one. Things like sort of people moving in at the beginning of the semester, you're meeting a lot of different people. Sort of once you fall into your class schedule, maybe you're having a more consistent group that you meet with. Things like that could all be things that might matter. Hard to say what they are, but hopefully we can capture some of the effects in a way that allows us to estimate transmission and prevalence more accurately, at least. So we're doing the testing ourselves. If someone tests positive, they get isolated, and we're the ones isolating them. So we know when the isolations occur. We know what we observe those times. We actually had like a contact tracing sort of squad we dispatched to your dorm to like come track you down and spirit you away to some isolation dorm. They didn't feed you at first, but they eventually sorted that out. Anyways, it's a bit rough at the first, but got that sorted out. And then of course, a big one I think that does matter is, well, imperfect testing. In particular, there are false negatives. For the PCR test, we were using false positives. I understand weren't really sort of that big a thing. Like generally, they wouldn't find any virus in your body if you had never been infected, if there was no virus. But false negatives could certainly happen. And in particular, we think it's dependent on the age of infection, because what is PCR measuring? It's measuring really your viral load, right? And so the viral load, we know, changes throughout the course of the infection. So testing accuracy should also change throughout the course of the infection. And lastly, kind of going along with that, well, probably more realistic to say transitions are not necessarily memoryless. Particular transitions from E to I and from I to R are not going to be memoryless. So it's not true that, like, no matter how many days you've been sick, you have the same chance of recovering the next day. It's not how it works, right? So generally, you get sick, you stay sick for a while, and eventually you recover. So we'll allow those things to be distributions to have sort of peaks somewhere and not just be exponential waiting times, or in our case, geometric waiting times for a discrete time model. All right. And then if we do this, so we can connect the survival function and the count model. So suppose I have the counts of compartments on time t. We'll say we're in discrete time here. So I have on day t, I have st, et, it, and rt. Those are the counts of my compartments. I have the population size n, and suppose that I also have this parameter beta s over time. Well, then define script st. What I say is, well, if you're an individual, you're currently still susceptible if you weren't infected on day 0, and you weren't infected on day 1, given you weren't infected on day 0, and you weren't infected on day 2, given you weren't infected on day 1, and so on and so forth, leading to this product formulation of this survival function here. So the idea is each term is sort of saying, what's the probability you didn't get infected on that day, given you also didn't get infected on all the previous days. And then that corresponds to the usual count model where you have the binomial count. So the idea is for each individual, what's the chance they were infected on a particular day? Well, there's, what's the number of new infections rather? Well, there were S sub t minus 1 individuals, and the chance that you don't get infected is this 1 minus beta t over n to the it. So the chance that you did get infected by at least one person or got contacted by at least one infectious person will be 1 minus that. And then the over n factor is often used for when you have a complete graph model, so sort of a closed well-mixed population. to scale things to be sort of appropriate in magnitude. The idea being if beta were order constant, I get on average fraction n, order n people infected every day. But what I really want is sort of order 1 people infected every day. So I divide by n. Okay, so let's talk about our data and estimation. So what do we actually observe? Well, we observe for all the individuals, all their test times and results, and their time of isolation if one exists. So if they could never test positive, that's one possibility. You could also test positive. If you do, you get isolated. We know when that happens. Then we're going to take as known the parameters phi governing transitions from E to I, and gamma governing transitions from I to natural recovery. I'll talk more about that a little bit later. And also this function f. F is giving you your test sensitivity, which depends on age of infection. And the goal is to estimate transmission, that's beta t, governing transitions from S to E. And then our prevalence is the compartment count. So I want to estimate the ST, ET, IT, and RT each day. And then, so if I want to consider imperfect test sensitivity, it's no longer enough to have, so back in my example here, I only had to have the most recent negative test and the positive test if one existed, right? Because if someone tested negative, I'm guaranteed they weren't infectious before that. If my testing is imperfect, this is not true. I don't have this censoring anymore, but I have sort of this imperfect censoring going on. So the idea being that now I have to have all the test dates and results, and I also got to keep track of the age of infection, because that information is relevant to, for one, deciding if a test is a false positive or false negative or not, and then also if somebody never tested positive, they still could have been infected, right? There's still some possibility they're infected. They just got a false negative, or for whatever reason it didn't test them in time, things like that, whatever happened. We're still going to assume transitions from S to I memory lists. You don't sort of like build up exposure by repeated contacts, but we'll take transitions from E to I and I to R not to be memory lists. They'll be sort of more centered at sort of what we think are the mean values of those types of transitions. And then a bit of notation. For each individual, we'll define capital DI to be the collection of tests for that individual, collection of tests and results. We'll say little ri is when individual I got isolated. We'll say ri is infinity if it never happens, or they never tested positive. We'll say delta I is when they enter the E compartment. And once again, we'll say delta I is infinity if it never happens. We'll say tau I is the length of individual I's exposed period, sigma I the length of their infectious period, and we'll say F sub I of S is the test sensitivity for individual I at infection age S. So a little bit much here, but just to have some notation so I can sort of write down the model and the estimation techniques. And then I'll drop the subscript when referring to the collection of all individuals. So for example, just like D by itself would be all the test results for all the individuals. Just R would be the time, all the times which all the individuals entered the isolation compartment, et cetera, et cetera. So I no longer have this perfect censoring. I got to think about the possibility of false negatives now. So what can I say about the time individual I was infected, my sort of survival function, my imputation function, given I'm now in this scenario? In particular, I want to think about what's the probability delta I equals T, individual I got infected on day T, given everything else. Given I know the test results, I have everything else here. And so Bayes' theorem says, well, it's the probability of seeing those test results for individual I, given everything else, appropriately normalized, right? So, and the idea here is that also, so note that if I figure out what delta I is, I estimate delta I, and I also know tau I, then I also know the time individual entered compartment I, because that would just be delta I plus tau I. And if I also know sigma I also know when they naturally recover. That would be delta I plus tau I plus sigma I. And so the goal is to use this sort of Bayesian structure to develop an MCMC to estimate this delta I and also the beta as well. So that's the idea. A bit more on going back to phi and gamma. So we're assuming they're known. Is that really realistic? Well, COVID wasn't at that time brand new. We have some idea of sort of what the typical incubation period is, what the typical sort of time you're infected is. So we had some idea, like from CDC guidelines, what these things might have been. And then I'd say about gamma in particular, it actually didn't really matter that much, because the idea is if testing is short of the typical recovery time, which it was for us, 7 versus 10 days, small changes in gamma won't really matter, because as long as your choice is broadly reasonable, most people are naturally recovering, doesn't really have much impact on the way that the epidemic unfolds. However, on the flip side, you could try to estimate, throw phi and gamma in the MCMC as parameters to estimate. But the flip side is then, well, there's also little information about gamma in the data. If it doesn't really matter, you're not really going to be able to estimate it in any meaningful way with any kind of precision. And then also, so I said previously here, I'm saying, well, I'm conditioning on this tau I and this sigma I. I don't know those things. That's true. But if I know phi and gamma, I know their distributions, I can use kind of my usual imputation / data augmentation technique for my MCMC here. So what do we actually do? Here's how things work. The idea is it kind of goes back and forth between the survival model using the beta and the count model using the survival function. Or other way around. But anyway, so the idea is I initialize my parameters. I have this S, I have beta, I have delta, I have tau, I have sigma, I have F. And so tau, sigma, and F we're taking just as known. And then, so I want to update by proposing the collection gamma, tau, sigma. So that characterizes the timings for all the events for all individuals, and thus also characterizes deterministically the compartment sizes at all times. How do I do that? Well, I propose tau and sigma just from their distributions. The idea being, if I know, once again, if I know phi and gamma, I can do that with my imputation. And then once I have all that stuff, I can propose delta I given everything else. And once I've got a proposed delta, tau, gamma triple for each individual, then I can compute the compartment sizes ST, ET, IT, and RT at all times deterministically. And then I have to do a metropolis step here. This actually is not quite the right conditional because, well, one way of seeing that is it doesn't stop me from proposing infections when no people are infected. Like I could have, people get infected on a day where IT is 0, but obviously can't happen. So I have to do a metropolis step to sort of fix that problem that I didn't actually, the deltas are not actually independent from each other, right? There's dependence in there. So I do a metropolis step to handle that. The acceptance ratio is very messy, so I didn't put it on the slide. It wouldn't have fit. It's in our paper though, if you're curious. And then once I have that, I can say, well, I have this count model for the number of new infections each day, depending on beta, and I can update beta t using the count model with the beta binomial conjugate prior model. So the idea is I'm going back to this here and using this model here to update via conjugate prior. And then once I have beta, I can compute S deterministically. So now at this point, I know beta t for all the t. I've drawn that. I've drawn my IT. I can just find ST deterministically. And so kind of the cool thing about this model is we're going back and forth between using S here to propose my triple, and then once I have the triple, using the triple and the count model to propose beta t. So kind of using both likelihoods. That's kind of the idea or the benefit of using this DSA formulation. Go back to step 2, do it over and over again as you do with MCMC, hope that it converges, right? So kind of your black magic kind of thing going on here. But actually it worked pretty well for us in practice, we found. Okay, so we first did a simulation study to check if things were working okay. So I generated some synthetic data using the following settings. I had 10,000 individuals over a 98-day time period. Those are picked and matched approximately what we had at Ohio State. About 10,000 students on campus at the time for about 3 months. The idea was, testing schedule was each week you got a random test day. So like every Monday, everyone got assigned a day of test randomly that week. And then if you test positive, you got removed 2 days later. That was based on what we actually saw in our contact tracing. Usually if someone tested positive, it took about 2 days to get 2 days to go track them down, put them in the isolation dorms. We gave beta t 5 change points to reflect behavior changing over the course of the semester. We took our tau I to be shifted Poisson with the phi = 3, corresponding to on average people are infected on average the incubation period is about 4 days. Then we said a sigma I was shifted Poisson, gamma = 10, so the average infectious period is about 11 days. And then we picked F to go from 0.8 to 0.9, peaking 30% of the way through the infectious period. That was based on some work by Larimore et al. Showing that viral load tends to peak early on in the infection. And the numbers 0.8 to 0.9 were kind of arbitrary, but chosen based on some meta-analysis showing the overall sensitivity of these tests is about 0.85. So that gave you about that value. So sort of based on literature, things we thought were at least broadly reasonable. And then the goal was to estimate in this scenario beta t and the prevalence of the counts of the compartments. That was the idea. So here's our simulation study results. We have the true prevalence. You can see we have two peaks, kind of cool, because that's coming from the change points in beta. So the idea was even early peak on, things kind of calm down for a while, but peak later on. Once again, you'll see a bit later, kind of matches what we saw at Ohio State. That's why I picked those settings. You can see the median's a pretty good estimate overall, and also the confidence, or the credible bounds here are pretty tight. I think we covered 94.9% of my data with a 95% credible interval, so about what you'd expect. So why are the credible bounds so tight? Well, because we have a lot of information. So you have sort of approximately censored observations of infection times. So you expect prevalence to be able to be estimated pretty well, I think. So not surprising that we can do pretty well here. And then we also estimated, I guess first, here's to compare to the naive prevalence estimator. So going back to that early slide, just here I'm taking to get the black line, just number of positive tests over number of tests each day. And then the red shaded area comes from your usual sort of point-wise binomial confidence intervals. So for one, you can see it oscillates a lot, overestimates these peaks by quite a lot here. And you can also see a lot more uncertainty coming from, well, I'm not using my sort of time series dependence information, so I don't do as well in that regard as well. So I think by throwing away the time series information, you're actually giving up a lot here. You get both the bias, but also you get a lot more variance because you're not using the information fully. And then here's the estimates of beta. So my true beta, I have sort of things start out moderate, get high, go lower for a while, get higher again, calm down. Once again, I picked those settings to kind of just get this curve that had two peaks. I wanted to see something that had sort of some interesting behavior like that. And you can see the estimate does pretty well, at least as far as when beta is kind of staying where it is for a while. Like when beta is relatively constant, we can estimate it pretty well. When it's changing fast, we're getting that it's changing, but maybe not the exact value. And a lot more uncertainty here, of course, because unlike prevalence, we're not getting sort of a censored observation of what beta is. We're estimating it from seeing the behavior of the epidemic. So a lot more uncertainty here. But we're following the pattern pretty well. And the median seems like a decent estimator when beta is stable over time, at least. And then, so we also had some real data. We ran this model from fall 2022. I think we stopped in, sorry, from fall 2020. I think we stopped in, let's see, fall 2022. The reason being that, so in fall 2020, compliance actually was very good. So students were taking things seriously, like we would probably say 95% plus. Students were doing what they're supposed to. But over time, students figured out that if you didn't comply, the only consequences, you got kind of a mad email from some person in the dean's office or whatever, and there were no further consequences beyond that. So over time, students were like, yeah, you know, COVID's over, bro. We're just going to go party. We don't care anymore. And so compliance kind of fell. And by the end, compliance was like 30%. And it's like, well, at this point, we're not really getting a lot of useful information. We're going to move on to other techniques here. I'm going to show you fall 2020. That's what we have an IRB approval for. So in fall 2020, we had about 12,500 students on campus. Our data includes the 11,645 who were at least 18 at the start of the semester for privacy reasons. Each student required a test weekly. And so we observe the test and isolation times for each individual. Once again, I'll take this tau I as shifted Poisson phi equals 3, sigma I as shifted Poisson gamma equals 10. And we'll take our F once again to be age of infection dependent, going from 0.8 to 0.9. Peaking 30% of the way through the infectious period. And once again, we're estimating beta T and prevalence. That's the idea here. Okay, so let's take a look at the results. So here are the results for our model estimate along with the credible bounds, and then the purple is test positive rate. So you can actually kind of see this oscillating bias here. It's kind of cool. See how it like goes up and goes down like this? Exactly what we'd expect for the naive prevalence estimator. We also had some issues involving sort of variable volume from day to day. Like it wasn't exactly the same every day. In particular, there were very few tests on Sunday. There were like Monday through Friday were usually pretty even. Saturday was like about half as much. Sunday was very, very little. Some of the wild days are probably Sundays. Like, you know, you get this sort of point way up here, or massive jumps. Like obviously the infection is not jumping from like, you know, 80 to like 200 in one day. It's just an artifact of small sample sizes. I'd also say here, you might be saying, well, why are the purple points not above your estimate? You talked about this upward bias. Well, I also didn't adjust the purple points for the possibility of false positives or false negatives. It's just the raw positivity, just sort of saying every day, what's the number of tests, what's the number of positives, divide that, that's my purple value. So actually, it's not clear here if it should be higher or lower than our estimate because they didn't account for the imperfect testing. I will in a minute show you that picture as well, but just to give you an idea of our model estimates just versus the raw naive positivity. And then if you adjust for the possibility of false negatives and build the confidence interval like before, here's what you get. So you can see now it is kind of true that the purple points are overestimating compared to our model, or they're higher at least. I don't know the truth here. I can't say for sure they're overestimating. So you can see once again a lot more uncertainty, and once again they tend to be potentially a lot higher. Like the peak here is once again like 40% higher than our peak. And even when things are small, and you can see it tends to be a little bit higher on average. Like the overestimation is proportional. It's not that big here, but it tends to be a little bit higher on average. And of course, a lot more uncertainty. The shaded red area is a lot wider. Now here's the estimate of beta. Of course, here I don't know the truth when you compare it to, but you can kind of tell yourself a fun story. The story we told ourselves is kind of like, students arrive at the beginning of the semester, they're like finding their new friends, they're all mixing together, meeting new people, going to events or whatever. Things kind of settle down, everyone's in the same study group again. And then towards the end of the semester, I don't know, there's more partying around football games, famously OSU plays Michigan around Thanksgiving time. That's always a big, partying time. People go out and do crazy stuff. So maybe that kind of thing is affecting things. Then toward the end, things maybe started leveling off a little bit again. The students started going home for Thanksgiving break. In our semester here, we ended at Thanksgiving break. After Thanksgiving, everything was just, we're done at that point. We're not going to come back for Christmas for like a couple weeks after that. After that, have finals or whatever. So it was a bit of a shortened semester. Is that actually what happened? No way to really know, but that was kind of our headcanon as far as why you might see this pattern. Okay, so talking about a few like limitations here. So I think one of them being closed and well mixed. Talked about before, maybe it's not quite as bad here as in like a general city, but still probably not exactly right. A big one was non-compliance. In fall 2020, not really an issue, but over time it got worse and worse. And a big question is, well, are those who are not complying different from those who are in terms of other behaviors as well that might matter? There's not really any way to know, right? Because you never get to observe them. But it seems like maybe they take more sort of risky behaviors generally. They're just sort of taking COVID less seriously. They're not as worried about it. I talked about, so not knowing gamma, not knowing phi. Well, probably, phi and gamma you might know, and also not knowing gamma doesn't really matter that much. But here I would say F, not knowing F is going to matter a bit more. It's going to affect things a bit more. And I think there's sort of less information about F compared to about gamma. Like most of what I was finding about F was just sort of saying, well, over tests in general, I get sort of a scalar value for overall sensitivity or whatever, but there was very little about age of infection dependent sensitivity that exists, at least at the time of writing this paper. I couldn't find very much about that. You can find information about viral loads, but it's not really clear how to translate viral loads exactly to sensitivity. Of course, over time, you get more pre-existing immunity. Like we have vaccinations now, people have been infected many times, so those things have to matter. If I were going to do this again, like in fall 2024, which we're not, hopefully, but those would all be things got to think about as far as so a lot of people will be vaccinated versus, or maybe have some pre-existing immunity from being infected in the past. A few more thoughts. So my example here was COVID. I think people are kind of done with COVID as far as it still exists, right? But we're not really taking it as far as it's not really an emergency anymore. We're living our lives again. We're not going to go back to like testing every student every week at Ohio State for COVID. It's not going to happen unless things get really, really bad somehow. But I would say IDSA is not strictly a COVID model. Our motivating example was COVID here, but it's not strictly a COVID model. I would say it's really just a model for anywhere where you have repeated testing in a closed population. And is that really a thing that happens? Well, I would argue yes. There are situations where that might be relevant. Things like I would say nursing homes, prisons, cruise ships could all be relevant. Things like say norovirus or the flu. Those could all be places where you could apply this kind of methodology because you have a mostly closed population there, and sort of outbreaks can get really bad because of that closed population setting. Like the famous barf cruise that they had where everyone got sick with norovirus, things those kind of things. How do you deal with those? So one option is some kind of regime like this. I think the framework is flexible for different modeling choices. I chose the F that I wanted to. I chose, whatever I wanted to choose. You don't have to make those choices. Like I chose, these to be shift to Poisson. That's not really important to the model. You can make them whatever you want. So flexible, I think. And then, like I was saying, I think repeated testing and isolation is not going to ever go away totally as like a useful tool for handling certain kinds of outbreaks and certain kinds of closed populations. A bit more context about future work. So I think a big question that came out of COVID that many of you probably are aware of is a larger effort to address the role of heterogeneity in infectious disease modeling. So like, your classic SIR curve, it's gonna, comet goes up, it goes down, and then we're done, right? So epidemic's over. That's not what happened when we saw COVID there, because there was heterogeneity. Things like differential people's frailty to the disease, differential behavior, pathogen strains, geography, timing issues. Like if you were in New York City, you got hit before people like in Ohio did. Like you could sort of see what was coming looking at the coasts in the big cities, right? Because where all the travelers come to from abroad. So all those things contributed to curves that could have multiple peaks, they could have plateaus, they could go up and down, have all these kind of behaviors. And so the question is, well, how can we address this in our modeling? And the big challenge, I think, is for one, well, some things like behavior are just sort of hard to observe in general. But even if you can, sort of throwing a million things in the model is probably not going to work very well. You'll have models that are overly flexible, estimation problems or parameters aren't identifiable. So how do you do this in a way where you sort of are able to get down and isolate, well, which kind of heterogeneities are most important? Which ones can I observe well? Which ones can I put in models to get practically usable results? I call them practically identifiable models. Like even with the DSA, we actually did a thing for the state of Ohio, and we had a change point model. And actually, there were issues around what I would call, you could prove it was identifiable theoretically. You could prove that, yeah, the parameters can be estimated. But we had issues with what I call practical identifiability. The idea being there were sort of parameter regimes that were far apart that would give you very similar results as far as the epidemic curve. And so how do I tell if I'm like in regime A or regime B? Well, the answer is you really can't, right? So what do? You got to think about how to make the model more constrained. Another question is the idea for data fusion or good data streams. So back in 2020, we're like grabbing all the data we can, data, grab it, bring it in. And there kind of was more data that people knew what to do with a lot of the time. It's kind of getting all this stuff dumped on you. And the question is how to thoughtfully combine different kinds of data. Like I think a big one's been environmental surveillance, say wastewater data. How do I combine wastewater data along with testing data to sort of do better than either one? Because they kind of have complementary strengths, right? So testing data is much more precise. You can see who tested, you can isolate the person, but it's subject to things like non-compliance, who's choosing to test, all those things are sort of relevant there, can bias it in various ways. It's much harder to opt out of the sewer system unless you're going to live off the grid and have an outhouse. Most people won't, right? So sort of wastewater is capturing all the people, but at a much coarser granularity. I'm not really seeing anything at individual level. It's only at this very large, like, the scale of like a town or a neighborhood or something like that. So can I use those two things to kind of compensate for each other's weaknesses? Another good question. Or also bringing in things like data from wearable devices or smartphones, tracking locations, behavior, whatever way we can, those kind of things as well, or social network data. Can we sort of combine all those things into individual models that are better than just using one by itself? Ongoing work, I think. So one project I'm involved in along these lines is environmental surveillance, not via wastewater, but via dust. So at Ohio State, once again, we were going into the dorms and they were vacuuming up the dust from the dorms, and you could look in the dust and look for people that are sick will shed viral RNA into the environment, right? So the idea was we go in and clean the dorms every so often. You can observe that dust, look for that viral RNA, and get a sense maybe for how big prevalence is at any given time. And so the idea essentially is that I have this observation window here where I'm observing dust. People are shedding virus into the environment. And so I model this via some ODE or some stochastic process. A viral RNA goes to the environment, some of it decays, and for us we use a thin Poisson process, but you can use like an ODE or whatever you want. The idea would be that here's what I observe at the end, based on the people shedding with different timings, my observation window, environmental decay, and then once I get that final observation, how can I connect it back to who I think was infected? That's kind of the goal of this project. The issue here is that, so the hope for dust versus wastewater is dust could be sort of more localized. Like for wastewater, I have maybe the entire campus. But for dust, you can say, I'm getting dust from like this building or this dorm or, whatever, this room even. So the hope was it could be a bit more precise. The issue is that it turns out that viral loads are incredibly variable. Like I was told by the virologists, like a plausible model for viral loads, sort of variation in viral load from individual to individual is uniform on the log scale, right? Which is massive amounts of variation. So that's saying like I expect to see orders of magnitude variation in viral load between individuals. So like I have this person really shedding it all, this person shedding a ton, right? That's kind of what you expect to see. And if that's the case, it's really hard to tell if you have sort of, one individual shedding a lot, a small number of individuals shedding a little bit, it's really hard to tell the difference. So I think it's hard to get estimates that are very precise from this. There's sort of ongoing work we're thinking about what we can do about this still, if anything, but interesting project. And sort of another flavor of environmental surveillance. many other interesting projects as well, I'm sure, but I think I'll end it there and open it up for questions. Thank you.
Great, thanks a lot, Matt. If you have any questions, feel free to drop them in the Q&A or in the chat. I will start something off, really interesting and thought-provoking stuff, but I'm curious, is there an application for this sort of a modeling in a decision-making sort of framework? You presented us results that looked at the whole course of the semester. Would this have been something that might have been useful in some way part of the way through the semester, perhaps at one of your beta inflection points?
Yeah, definitely. So we actually had this model running kind of in real time. Every day we'd update it, right? And so there were a couple of things we were looking at. One of them was a big concern at Ohio State was you have these isolation dorms, right? And if the isolation dorms kind of got overran, we ran out of space, and everyone has to go home. That was kind of like the catastrophe scenario we were trying to avoid. So a big decision-making point was like, do we have to get more isolation space, things like that. Do we want to increase the frequency of testing? We had a couple weeks, and I think it was in the spring, I believe, we tested twice a week to try and further reduce prevalence and transmission, kind of get things tamped down when things are starting to go peak up. We were doing short-term predictions. I think if you believe beta is changing a lot, long-term predictions don't make a lot of sense. Predicting out 10 days a week, we're usually doing that. The idea being try and predict like next week how many isolation rooms will we need, that kind of thing. So it was going into all those decision-making processes, I would say, yeah.
Yeah, and I guess it's sort of beyond the scope of a model like that, but you could imagine an extension that might incorporate some of the cost of the testing in to adjust the testing rate as you're going along.
It was kind of hard to get good information from our testing provider. Like, for example, we asked them, what do you think sensitivity is? And they said, well, we did 6 tests and they're all right, so it's 100%. Like, I don't know if I believe that.
Right. I guess the thought is that if you start seeing an uptick in transmission, you might want to test even more frequently. But then as
yeah, we did a couple times actually do that.
Yeah. So on a related note, the question of subpopulations. You sort of mentioned it's similar to what you suggested in terms of the dust and looking at what's in the dorm, but could you break this up? Because I'm assuming in the fall of 2020, say the students were probably spending more time in their dorms than they might have been in quote a usual or typical semester. So would it have made sense to do a subpopulation analysis based on living arrangements?
Yeah, so we actually built one based on campus versus off campus. Like a lot of students at Ohio State live off campus, right? So we built the mechanism for this, tried doing it. The issue was our information about off campus students was like really bad. Like it was really very little information there. We found actually it wasn't really making things any better as far as estimation and prediction, but kind of shut that down eventually. So I think, yeah, you can do it, but we have to have, in our case, better information about whatever our subgroups are, I would say, for it to actually be effective.
I guess I was just even thinking of specific dorms, right? So
I see.
One hypothesis is that a given building might be a potential hotspot, as it were, in a way that might transmit before you could catch it. So, would any information like that be useful?
We never tried that. It's a good idea. I mean, part of sort of as it was ongoing, one limitation was kind of time we had. We were kind of, I would say we were driving, we were building the car we were driving, as like to say. So a lot of cool things we should get back to and think about. Definitely, I think that's a good idea.
Yeah, of course, right, and that's not to a criticism in any way, but just sort of trying to think about how this data model like this might be more useful in the decision-making process.
Yeah,
and it's really a pretty unique kind of thing to look at a college campus as this place where you do have this ability to get at least some hope of getting that kind of fine granularity of information that is very different, say, than from if you had a bunch of people who were living in, say, apartment buildings of similar size and density at the same time. You might not think of them as in quite the same ways you would as college students, as quite this community. And so it does give you a lot that you can look at. And plus also, even if the testing regime wasn't terribly well enforced, you do have some levers that a university can move,
Mhm.
right? That also give you this other. So you had a really unique sort of playground for the models there.
Yeah, it's a really interesting data set for that reason, kind of unusual in a lot of ways.
Got it. So any other questions from the audience? And I'll also just ask the other question of you touched on this a little bit, but any other future directions you have for building on these models?
I'm really interested as far as like things like behavior. So I think I've also been working on the probabilistic side, thinking about kind of the classical contact process models where you can prove, various results about when you have like epidemics versus when you don't. And I think a big frontier there is behavior. So if you have the classic sort of SIS, SIR model, and you don't have any behavioral things going on, one sort of nice thing that happens is in these models you get monotonicity, where the idea is more infection now only ever, at least in a stochastic sense, leads to more infection later, right? That makes sort of it easy to find things for upper or lower bounding processes, sort of make sort of estimations in that way, right? But if you add things like people can self-isolate, they can, get quarantined, things like that, that can change that fact. So the idea is maybe like more infection now leads to like more self-isolation now leads to less infection later, right? So how do you deal with that? And a lot of the tools people have derived to analyze the classical contact process or the SIS, SIR models don't work anymore. And so thinking about how do you understand those models in different ways, I think is a big area of interest for me.
Well, it seems like you might be able to do something with that with the OSU data if you had it, because you mentioned the football game. So did you see a spike in cases after the football game?
Yeah, that was the second spike around. That was our theory, at least. Second spike close to Thanksgiving was football game related. We thought. So yeah, definitely. But sort of part of the task too is deriving the actual model itself. I think as well is actually a challenge because a lot of the approximation techniques that you use for the SIS SIR model don't work anymore, or at least have to be reproved with different techniques.
Yeah, absolutely. So what you don't know is how many of those people actually went to the game versus some of their behavior. But you could approximate that, I would imagine, but based on some historical data, perhaps. But
yeah,
X% of the people go to the game every year or something. Interesting. Sounds really great.
Thanks.
One last call here for other questions. Well, not hearing anything, I guess we'll close it up. Thank you, Matthew, for a nice talk. Really great work, and look forward to hearing more of it. And we will be back. Kristen, we have a special, believe we have a special rescheduled webinar coming up in, is it next week?
Yes, it's next.
Yes, April 5th.
It's next Friday.
Right.
It's the 5th, yeah.
That will be Sherry Z from the University of Pennsylvania talking about the incorporation of queuing theory to a spatial optimization framework to improve mass vaccination campaigns. So please join us the same time next Friday for that talk. And otherwise, thanks everybody. Have a great weekend.
Thanks for having me.
Oh, thank you. Appreciate it. Take care.
Yep. Take care, everyone.